Imagine an object so dense that a single teaspoon of it would weigh billions of tons. Imagine a stellar corpse, the collapsed core of a giant star, crushed into a sphere barely the size of a city, but with more mass than our sun. An object with a gravitational field about 200 billion times stronger than Earth's. Now, imagine you're falling into it. Your journey would be over in an instant, but the moments leading to your spectacular end would be the most terrifying and violent in the entire universe. It's a multi-stage process of annihilation, a deconstruction so absolute it operates on scales both cosmic and quantum. First, you'd be stretched into a stream of atoms in a process nicknamed, almost playfully, spaghettification. Then, those atoms would be obliterated on impact, releasing a burst of energy that would dwarf all the nuclear weapons on our planet combined. This isn't just a fall, it's an erasure. So what really happens if you find yourself on a one-way trip into the heart of a neutron star? Before we begin our terrifying descent, we have to understand the object of our demise. What is this cosmic monster waiting for us in the dark? A neutron star isn't a star like our sun, a brilliant, life-giving ball of fusing gas. No, a neutron star is what's left over after a massive star, at least 10 times the mass of our sun, dies in a cataclysmic supernova explosion. For most of its life, that giant star was in a delicate balance. The outward pressure from nuclear fusion in its core fought a constant battle against the inward crush of its own massive gravity. But when the fuel runs out, the fire dies. Gravity, patient and relentless, finally wins. The star's core collapses with unimaginable speed, and the temperature skyrockets. In this inferno, atomic nuclei are smashed apart. Electrons and protons, the building blocks of matter, are forced together under such extreme pressure that they merge to form neutrons. The entire core of a once mighty star is compressed into a ball of nearly pure neutron matter, a city-sized atomic nucleus. The result is one of the densest objects in the known universe, second only to a black hole. Its density is so profound that the escape velocity from its surface is more than half the speed of light. The matter it's made of, sometimes called neutronium, is kept from collapsing into a black hole by a quantum phenomenon called neutron degeneracy pressure, aided by repulsive nuclear forces in more massive stars. This pressure is a strange but powerful outward force where neutrons essentially refuse to occupy the same space and state. And they spin fast. Thanks to the conservation of angular momentum from their massive parent stars, neutron stars can rotate hundreds of times per second. Some, called magnetars, possess magnetic fields so ludicrously strong they could wipe a credit card from the distance of the moon. It's a field capable of distorting atoms themselves and warping the very vacuum of space. This isn't just a destination. It's an environment where the laws of nature are pushed to their absolute breaking point. It's a cosmic tombstone, unimaginably hot, absurdly dense, and spinning with a fury that can last for millions of years. And it's into this environment that our journey takes us. Let's set the scene. You're an astronaut, farther from home than any human has ever been. Maybe it was a nav computer glitch, a critical engine failure, or just a science mission that went horribly wrong. Whatever the reason, your ship has drifted into the gravitational grip of a neutron star. From a distance, you might not even see it. A neutron star is tiny on a cosmic scale, maybe only 12 miles across, a pinpoint against the black. You wouldn't see a glittering star, but you would see the bizarre effects of its presence. The light from distant galaxies behind it would be warped and bent, an effect called gravitational lensing, making the cosmos shimmer and distort around an invisible point. Your ship's sensors would be screaming. Alarms for gravitational shear, X-ray radiation, and magnetic flux would all be blaring red. Even an old, isolated neutron star is still searingly hot, with surface temperatures in the millions of degrees, bathing the surrounding space in high-energy radiation.
You try to escape. The main engines roar to life, pushing with all their might against the invisible tether that's caught you. But it's already too late. You've crossed the point of no return, where the gravitational gradient is so steep that no amount of thrust can pull you away. The escape velocity here already exceeds your ship's capability. The engines strain, then fail, and your ship begins its final, unstoppable fall. The fall itself is astonishingly quick. Gravity here isn't the gentle pull we feel on Earth. It's a voracious, consuming force. If you dropped an object from just a meter above the star's surface, it would hit at around 1,400 kilometers per second. Your ship, falling from much farther out, will accelerate to a colossal speed. By the time it reaches the star, it'll be traveling at a huge fraction of the speed of light. But you won't make it to the surface in one piece. Your ship won't, and neither will you. The true horror of this fall isn't the impact, it's the journey. It's what the star's gravity will do to you long before you ever get there. The process that will destroy you has a deceptively playful name: spaghettification. We're familiar with a gentle version of this tidal force here on Earth. The moon's gravity pulls a little more strongly on the side of the Earth facing it than the far side, and this difference creates our ocean tides. Now amplify that by a factor of 200 billion. As you fall feet first toward the neutron star, the gravity pulling on your feet is astronomically stronger than the gravity pulling on your head. This isn't a small difference. It's a chasm of force across the tiny length of your body. It would start as a strange, persistent stretching sensation. Not painful at first, just deeply unnatural. But it would intensify with terrifying speed. That gentle stretch becomes an irresistible pull. The forces holding your body together, the strength of your bones, the elasticity of your skin, the bonds of your very cells, are no match for the star's lopsided gravity. This is spaghettification. Your joints would be the first to go, dislocating as the lower half of your body accelerates away from the top half. At the same time, your body would be squeezed from the sides, compressed inward as every particle is pulled toward the star's center. You're being stretched and squeezed at the same time, extruded like pasta. In a blink, your bones would snap. Your tissues and organs would tear apart. You wouldn't even have time to scream, not that sound could travel in a vacuum anyway. The nerve signals from your stretched body wouldn't have time to reach your brain before your brain itself was being unmade. Your body, a complex machine that took billions of years of evolution to build, is unceremoniously reduced to a long, thin stream of organic matter. This all happens hundreds, if not thousands of miles above the star's surface. You are comprehensively destroyed. You're no longer a person. You're not even a body. You're a tenuous ribbon of molecules, still accelerating at a blistering pace. But the violence is far from over. What happened to your body is about to happen to your atoms. The stream of organic matter that was once you continues its death spiral. The tidal forces that tore you apart don't stop. They keep working, reaching down into the fundamental structure of your matter. The chemical bonds holding your molecules together are the next to go. The spaghettified stream of proteins and water is ripped apart into its base molecules. Then those molecules are themselves torn asunder as the gravitational gradient overwhelms the forces that bind atoms. You are now a stream of individual atoms: carbon, oxygen, hydrogen, nitrogen, the building blocks of your life, disconnected and hurtling through the void. But even this state is temporary. The star's environment is a maelstrom of high-energy particles and X-rays. Its immense magnetic field can strip electrons from their atomic shells. Your atoms are ionized, their electrons ripped away, leaving behind naked atomic nuclei. You are now a plasma, a superheated soup of atomic nuclei and free electrons that was once a thinking, feeling being. Still, the fall continues, faster and faster. The tidal forces persist, now working on the atomic nuclei themselves. The force difference across the tiny diameter of a single nucleus begins to rival the strong nuclear force, the glue that holds protons and neutrons together.
Finally, the very nuclei of your atoms are stretched, distorted, and torn apart. You are reduced to a shower of fundamental particles: protons, neutrons, and electrons. This is total deconstruction. Nothing of your original form remains. You have been rendered down to your most basic subatomic components. This cloud of particles is all that's left of you, and it's this final elemental form that will make the impact. The ghost of you, this stream of subatomic particles, finally arrives. But what is the surface of a neutron star? It's not something you could stand on. The outer layer is a crust, thought to be made of atomic nuclei like iron, crushed into a solid lattice 10 billion times stronger than steel. It's a crystalline solid arranged in bizarre structures that physicists have nicknamed nuclear pasta, with shapes resembling gnocchi, spaghetti, and lasagna formed by the immense pressure. Your remnants, accelerated to a massive fraction of the speed of light, now slam into this impenetrable crust. The impact isn't a collision, it's an event of pure energy conversion. The colossal kinetic energy carried by your particles is transformed instantly into heat and radiation. The result is an explosion of unimaginable scale. Even a single marshmallow dropped onto a neutron star would impact with the energy of a powerful bomb. The mass of your body hitting at such a speed would trigger a titanic blast of gamma rays and X-rays that utterly dwarfs the entire nuclear arsenal on Earth. It would be a flash of pure energy erupting from the star's surface, brief but more powerful than anything humanity has ever created. The matter that was you is now part of the star. Your protons and electrons are likely crushed together to form more neutrons, adding an infinitesimal amount to the star's mass. Your constituent parts are now part of the neutron-degenerate superfluid in the star's core, or perhaps sink even deeper into a theoretical quark soup. Your fall is over. Your matter hasn't just been destroyed. It has been fundamentally changed and assimilated into one of the universe's most extreme objects. You have become a footnote in the life of a dead star. Your end marked by a cosmic firework that blazes for a moment before the neutron star returns to its silent, menacing vigil in the dark.
The cosmos is full of terrifying and awe-inspiring power. If you find the stuff as fascinating as we do, make sure you subscribe and hit the notification bell for more journeys into the unknown. And let us know in the comments what cosmic what-if we should explore next. The journey from a thinking being to a flash of gamma radiation is a story of incredible scales. It's a reminder that the forces governing the universe operate on levels of power that defy our everyday understanding. Falling into a neutron star is a lesson in humility, demonstrating that the intricate structures we call life, and even the solid matter we take for granted, are fragile constructs, easily unwritten by the fundamental laws of physics. You are erased, but your fall serves as a stark illustration of the universe's raw power, a power encoded in the unbelievably dense heart of a long-dead star.